if we zoom in, and we want to know that green vector, which is going to be the displacement vector, right? If I want to know what it is, I could look at it as being the unit tangent vector. Remember what the unit tangent vector is? If you have a curve, right? You have a curve, you have a unit tangent vector, which is a vector that is tangent to the curve and has a length of what? 1, right? So I take that would be too big because that's just going to have a length of 1 the whole time, right? So what I do is I scale it back and I scale it down to the infinitesimal arc length at that point. So I scale this by ds. Remember, ds is that infinitesimal arc length. So we're zooming in. We zoom into that, and we've got our red vector coming off here. That's our force. We've got our point, and that point is moving along, right? The curve right there. And I'm taking this little infinitesimal length, the arc length, and I'm scaling, using that as my scalar to scale my tangent vector back to that size. So the tangent vector gives me, the unit tangent vector gives me a direction vector with a unit length, and the ds just shrinks it down to be infinitesimally small, but still pointed in the direction I'm headed. Is that too much? Does that make sense? Visually, yes?
Is this like infinitesimally, or never mind.
Well, the integral is going to make this go down to nothing, right?
Right.
Okay. So it's like the dx was, right? It's like dx has been with rectangles, except that it has a different geometric meaning now because this is actually our displacement vector. It's some scalar multiple of our unit tangent vector. So that's the work done at each point. It's the force dotted with the scalar multiple, infinitesimal scalar multiple of the unit tangent vector. And then we just need an integral to add them all up, right? We just need an integral to add them all up. So this is what the work would be. It would be the line integral. Why a line integral? Because you're moving along a path, right? You're moving along a path. And it's going to be the force dotted with the unit tangent vector times ds. Yes?
What does the dot product do with the integral?
Exactly what you would think. It's going to take two vectors and dot them.
Integrate them and then dot them afterwards?
No, you dot before.
You dot before?
You dot before. Because remember, when you take two things and dot product, you get a number, right? Or you'll get some scalar function. Two vectors dotted doesn't result in a vector. It results in either a number or some scalar.
But you dot and then integrate?
Yes, absolutely. All right, so we still have more to develop the formula, all right? So we've got, this is our formula for work. It's the dot of F and the field and the unit tangent vector, and that's the arc length formula. R of t is the vector function that draws the curve, right? R of t draws the curve, and t is restricted between A and B. So we draw, start, stop, right? So what we're going to do now is we're going to mess with this formula, okay? Remember that back in earlier chapter, the unit tangent vector is defined to be the derivative of the vector function that draws the curve. It's the derivative of that divided by its own length. That's a definition we had a long time ago, right? And then also remember, we just defined this a second ago, or last class and today. This right here is that square root thing, right? The square root of the derivative squared. That's that thing, the magnitude of the derivative of the vector function dt. That's what ds was. That's our little arc length formula. If we put those side by side in this formula, right? This right here is this. This right here is this. And do you see what happens? These cancel, right? And so what you're left with is the vector field dotted with what? The derivative of your curve, right? This is gone, that's gone. So this is your vector field evaluated along your curve, dotted with the derivative of your curve, dt. That is what will get you the work done. This is the most important formula right here, this one. And I summarize it with a final boxed version, all right? Suppose you have a vector field. Suppose you have a vector field. Now it has to be continuous. There are some restrictions because vector fields can be weird. They can have like singularities and stuff. So this is a nice vector field. And your curve is smooth. We don't want any crazy curves, all right? As long as we've got some conditions met here, then the line integral of the vector field f along C is this. This calculates work, but more generally, we call it the line integral of the field f along C. Here's the new notation. Here's the new notation, right here. This is new. When we started class, I think everybody hopefully understood what this meant. This was the line integral along C with respect to arc length, right? This is the line integral along the field, right? I'm sorry, it's the line integral of the field along C. This is just notation. Do you see that this notation makes sense for that formula? It's the f dotted with this thing right here we're calling dr now. dr, but with the vector on the r. Yeah?
For our specific example, what exactly is the R?
For the example that I just drew, the parabola.
Okay, the parabola.
The path you tried to move through the field, right? That's going to be your r of t.
I was thinking it was that, but I just wasn't sure.
Yep. All right, one last thing. If you reverse the path, you reverse the value of work. So if you reverse the path, you're going to change the sign of your answer for this particular computation. All right, let's do this one. We're still in 13.2.
Good Lord.
Yeah, it's a massive section. Find the work done by the gradient vector field. Find the work done by the gradient vector field of f of x, y equals x plus y, that quantity squared, on a path traversing the top quarter of the unit circle in the counterclockwise direction.
That is certainly a combination of
Yes.
So the unit circle from pi of 4 to...
Just top quarter, top quarter, not top eighth.
Yeah.
Our curve is
like that.
that. Top quarter.
0 to pi over 2.
0 to pi over 2.
So that's the top quarter?
Yep.
Okay.
Yeah, because there's 4 quadrants, so this is a quarter of it.
Yeah, but the other side's also equivalently top.
Oh, yeah, I see what you're saying.
Yeah.
I think I highlighted this because I want to be specific. I'm talking about that top quarter.
Gotcha.
Yeah. You're saying you could be talking about the second quadrant.
Yeah.
Okay,
Which was
yeah,
why
I
was
agree.
thinking, did you mean like rotated 45 degrees?
I hear you.
Because that would make it a
This drawing,
Yeah.
this drawing.
Gotcha. I understand.
So is unit circle? Yeah, unit. So this is 1, 0, and this is 0, 1. All right, so we want to traverse this, right? We want to traverse it in that direction. Do you think you could, I mean, right now I think all I'm doing is focusing on trying to come up with r of t, the thing that draws the curve. I'll worry about the vector field and all that in a minute, right? So r of t, I can draw this using the vector function cosine t, sine t, because we've beaten this to death. T is going to go between 0 and pi over 2. Right? Okay, so I've got my vector function that draws that curve. Happy with that. I'm trying to find the work done. Don't I need a vector field to do work? Don't I need a vector field? Do I give you a vector field?
Yeah, it's the fx x y.
Is that a vector field? That's not a vector. How do we turn it into one? The gradient. So read the wording. Find the work done not by this scalar function, by the gradient vector field of that scalar function. So you have to generate the gradient vector field now. So what is the gradient vector field? The gradient of f is the field the vector field, how do we do gradients again? It creates a vector. It's partial of that f with respect to x. What's partial of that with respect to x?
2x plus 2y.
2x plus y. Yeah, and then you could distribute the 2, right? That's the partial of it with respect to x, comma, the next component of the gradient vector field. Isn't it the exact same thing? Any questions on what I did there? The gradient of the scalar function is the vector created from the partials. So this is partial of f with respect to x, comma, partial of f with respect to y. That's what I just did right there. Chain rule. Okay, so do we have a vector field?
Yeah.
Yes. Do we have a curve that we're going to move through? Yes? Okay, so if we have that, we should just be able to crank the formula. So here's our formula. Right there. Moving this down just a little bit. Okay, so here's what I'm going to do. I'm going to do this right here, right? I'm going to do the integral from a to b. Now, a to b are the limits for the variable t that draws the curve, right? So that's going to be 0 to pi over 2. And then here's some strange notation again. The vector field with the curve plugged in. What that means is take this vector field and replace the x and y with the x and y from your curve. This is the x, this is the y off your curve. You only want that field as you move along the curve, right? So this restricts you to the curve. And it is a vector still. It is the vector 2, parenthesis, cosine t, what? Plus sine t, comma, and then now 2, same thing, right? Cosine t plus sine t. Okay, I'm going to highlight this so you know what it is. This right here is that right there. What are we doing with that?
Dotting it with the derivative.
Dotting it with the derivative of that. So I need to now take the dot product of that with, and I'm kind of out of room here, but I'm going to squeeze it right in here, with the derivative of r. Here's r, right? The derivative of that is another vector function. It's negative sine t, comma, cosine t. And then all of that dt. And that actually looks worse than it is because, remember, dot products were much easier than cross products, right? Dot products, you just multiplied the first components together, then plus the second components multiplied together. So I'm going to do that now. And this is, this right here is that right there, right? I'll put it here. Integral 0 to pi over 2. All right, when I dot, I'm going to take this and multiply this right there. Ugh. I'm going to try and do it all together. All right, I'm going to try and do it all together. So I'm going to do the negative sine t here. I'm going to distribute the 2 through as well. So I should get negative 2 sine t cosine t minus 2 sine squared t. All right, isn't that what I would get? If I hit this with a negative sine t, and then pass a 2 through, I should get that. And then I have, because dot product says now plus, right? Plus now the y parts multiplied. So when I do the y parts, I'm now doing this times this. And kind of the same thing happens. I do cosine here, and then I pass a 2 through. So 2 cosine squared t, and then plus 2 cosine t sine t. And that's all, right?
Okay.
dt.
Cosine t, sine t, combos cancel each other out.
Yeah, we do get something to go away at least, right? This is gone, this is gone. Unfortunately, that's not Pythagorean because one of them's negative, the other one's positive, right? You can pull a 2. Let's go ahead and do that. We'll pull a 2 out. Integral 0 to pi over 2. I want to get to this to a point that you feel like we could take it the rest of the way, right? So if I pull out a 2, I'm left with this without the 2's, right? I'm going to write it in reverse order. Cosine squared t minus sine squared t. And then somebody who's like really sharp with their pre-cal recognizes that as a double angle formula for cosine. So this is, where is it? Hold on. It's what? Cosine 2t. Yeah. I'm going to bring it up here. Here we go. I thought this was the formulas. What the hell? Here we go. Here it is. Zooming in. There it is. Cosine of 2x is cosine squared x minus sine squared x. That's what I'm using now. So this just becomes 2 integral 0 to pi over 2 of cosine of 2t dt. And I think at that point it's kind of trivial. But hey, you know what? We're here. Let's just do it, because that's such an easy antiderivative, right? So the antiderivative of that's going to be 1/2, right? 1/2 sine 2t. And then the 1/2 hits the 2. So that should just be sine 2t, evaluated from 0 to pi over 2. And if you plug in pi over 2 into this, you get pi, and sine of pi is 0. And if you plug in 0, you get 0. Sine of 0 is 0. So you get a total work of nothing. And that's only because of the symmetry of the problem and the symmetry of the field. We're relying on that because you're not generally going to get... Where the hell is it? Oh, here it is.
What is 0 working?
Pardon me?
What's 0 working?
Well, it's like you're working, sometimes you're working with, right? The force is actually helping you, right? It's like if you move something up and down, right? You have to work to move it up, but to go down, it doesn't.
Like a 0 sum.
Like a 0 sum, yeah. It's a 0 sum.
I worked hard, but I worked easy here.
Yeah, yeah.
If I move if I move a chair over there, then move it back at a total sum of 0.
Well, no, that wouldn't be, because you're not, this is, the field here, this is like gravity, right? It's like, you know, when you go down, it's like you don't have to do work, right? Pardon me?
It only works for like forces like 10
Yeah, there's certain conditions we would have, right, to ever get a work of 0. Like there's certain things have to happen. We're going to talk about conservative vector fields because, like I told you before, those are the most like relevant ones to us. What do we got here? That looks terrible, doesn't it?
Yeah.
What's that? This should be the last.
The last problem we ran out of time.
It is. Depends on how fast I do it, though. So here, I'm asking, do I say find a work? Am I saying find the work?
No.
In some sense, yes. In some sense, no. Because this, in the mathematical realm of things, in the world of math, this is simply the integral, right, of the vector field C along the curve. Of the vector field F along the curve C. Now, in physics, if you got, some sort of force and displacement, then you're talking about work. But in mathematics, it's more general. It's more abstract. So we're going to try and find this line integral, or this integral of the vector field along this curve C. And it's the same formula we just used. So we need a field. Do we have a field? I gave you the field this time, right? You don't have to calculate the gradient. It's just, there's the field. And then I have a parabola for you. So let's parameterize the parabola. That parabola looks like this. 1 plus x squared, and we're going from -1, 2 to 1, 2. 1, 2, yeah, 1, 2. We're going like this. We're moving along there. So we're moving this point through this field. And you can look at that as now we're saying, you know, what amount of work was done to move from here over to here. And I need to find the vector equation, the parametrization, the vector function that draws that. And because that is solved for y, I'm just going to go t here, and then here I'm going to go 1 plus t squared. Right, that's using this. And I know that t has to go between -1 and 1 because that's my restriction on the t, which is my x coordinate. Good with r? Any questions on r? All right, so my line integral, or my integral, is going to go from -1 to 1. All right, the field is a vector, but it's not that vector. It's not this vector field with x and y in it, right? It's with that stuff in it, right? So x gets replaced with t, and y gets replaced with 1 plus t squared into here. So t over square root of t squared plus 1 plus t squared squared. X, square root of x squared, and then that's your y, right? Your y, and then the square it. That's the first component of the vector field. The second component is y, which is 1 plus t squared, over square root of x squared, which is t squared, plus 1 plus t squared squared. This is looking horrific, right? Isn't that looking horrific?
Maybe we can change coordinates instead of.
I'm going to dot that, right? I'm going to dot that with the derivative of this, right? The derivative of this, right? I need to take derivative of this. So derivative of this is going to be what? 1, 2t. 1 comma 2t. We're doing that with respect to t. All right, now do your dot product. When I do 1 times that, I just get that. So I just get t over the square root of t squared plus 1 plus t squared squared, plus now when I do 2t times that, the 2t distributes through the top, right? 2t distributes through the top. So I get 2t plus 2t cubed over that same denominator. dt. No problem, right? Looks pretty straightforward. Let's put it together. I have a feeling something good's going to happen. Okay, if I put it together, on the top I've got 2t cubed plus 3t. And on the bottom, I have the square root of dt. Let me actually expand this. If I were to multiply this out, what would that be if I fold that out? 1 plus 2t squared plus t to the 4th, right? Pardon me? Oh. That's what that would be, right, if I expanded it? And then I added t squared. So it become 3t squared there? Add that one. So on the bottom here, I have t to the 4th plus 3t squared, yeah? Plus 1. Think we could do it with the u sub? Is that just a basic u sub? Is it? Could it be? Could it be? I mean, I sure as hell don't see what else. All right, look, if u is the entire radicand, what's the derivative of that? 4t cubed plus 6t, right, dt? Is that what we have up top? Oh, if we pull a 2 out of this, we do, right? This problem was tailor-made so it works, all right? Do you all see that's just a basic u sub?
Yes.
Okay. We're done with the problem. You can take it the rest of the way.
That's it, that's class, right?
Yeah, almost done. We have one more problem to do. We still have 9 minutes.
You gotta pack more in there, man.
It's an odd function, so it's 0.
Pardon?
It's an odd function, so it's 0.
Is the bottom odd?
No, it's an even, but it's an odd times an even, which is an odd.
So this right here is odd. I mean, sorry, even.
The top is
This
odd,
is
the
odd.
bottom is even.
So even doesn't have any impact on
Odd function.
odds. So yeah, that would be 0.
Yeah, it's symmetrical.
Yeah. But do the U sub because it may not always work out that way. But that's a great thing to notice. All right, last one. Maybe. £180-pound man carrying a 20-pound tool bag walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured in foot-pounds. Also, weight is a force. All right, so let me show you the picture of what's happening here. I think you can kind of get the idea. You've got a person here. Here's a cylindrical silo. You have like a helix staircase going around, and this person is going to walk up the staircase, right? It's going to take 3 complete revolutions to get to the top, right? So 6 pi, right? Now, we want to know the amount of work done. Now, I know some of you have taken physics and realize that the only thing that matters here is his vertical displacement. That's all that really matters. But we're going to do this from the mathematical perspective because we don't want to limit ourselves to just certain scenarios, all right? So what I'm going to do here is I'm going to start by seeing if I can figure out what the field is. What's the field? Well, the only force acting on this man is what? Gravity, right? So gravity is a force that goes down, yes? So to do the work he has to do has to counter that. So his force is basically his weight plus his bag. That's our field, and it's pointed, we'll say, upward, all right? So he just has to, that's the only force in play here is a up-down force. So my field is this vector function. Now, you could use negative 200 if you wanted to argue with me that, you know what, let's look at gravity as being positive and then his work is going against it and be negative. You can use either 200 or negative 200. You know, we could argue that. I'm going to use 200, all right, because he has to counter gravity, so the work is going to be, the force is actually upward, 200 pounds against the gravity down. Got it? You agree that's the field? Buy that?
Yeah.
All I need is R of t. I need to draw the helix that goes around. Now there's some important things here. I said it had a radius of what? 20 feet. So looking at the helix, or looking at this from the top, right, just top down, you just need to keep drawing a circle over and over and over, right? That's all you have to do, which we can use cosine and sine for, but we do have to adjust the radius, right? The radius should be what?
20.
20? So R of t should be 20 cosine t, 20 sine t. Oh shit, I forgot that I have to be somewhere. Damn it. I forgot, I was gonna tell you I need to leave at 2:35. We're gonna call it, sorry. I gotta go. I forgot I have to be somewhere. So we'll pick up right here. We'll pick up right here. The important thing of this problem is try and figure out what's happening here. And the way you do it is you unwrap you unwrap his path. Unwrap it. If you unwrap his path, you basically can look at it as him going up an inclined plane. And you know that he travels 90 feet vertically. And then you can somehow set up a ratio to figure out this function. So we'll do that next class. It's not that bad.
It looks bad.
But would you be able to use the arc length formula to find Z as well?
To find what?
The Z.
To find this? What you...
Oh, couldn't you use circumference and then just triple it?
Oh yeah,
You-
it's so sad.
You could make it, you could do it with a lot of things.
It's the lever.
I think the easy